The first thing that we are going to talk about today is instantaneous power. What we do in steady state sinusoidal systems. No. So let's say that I have a generic black box element or network over which a voltage V of t appears and through which a current of I of t flows through. By definition, the instantaneous power absorbed by this element will simply be the product of the current and voltage. When V of t is of the form Vm cosine omega t plus theta v, and I of t is of the form Im cosine omega t plus theta I, the instantaneous power absorbed by this element is then obviously Vm cosine omega t plus theta v multiplied by Im cosine omega t plus theta I. And I can use a trig identity that says cosine angle 1 times cosine angle 2 is equal to 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. To rewrite this expression as 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. So this is our generic representation of instantaneous power, okay? This is a time domain quantity because we have a dependence on t here, but it is made up of phasor components, right? So Vm and theta v are the magnitude and phase angle of the phasor voltage drop across our network. Im and theta I are the magnitude and phase angle of the phasor current flowing through our network. So we can do all of our analysis in the frequency domain and then take the results of that frequency domain analysis, plug it into our time domain function, and get an understanding of how the power absorbed by this device varies as a function of time. Okay. We can see pretty easily, or at least I hope it's pretty easily, that this first part here is a DC contribution to the power because Vm and Im are both constant quantities, theta v and theta I are constant quantities, and so the cosine of a constant angle is literally just a number that ranges anywhere from +1 to -1. Okay. So we have some DC term, and then superimposed on top of that DC term, we have this AC term. So if I were to plot power as a function of time for a generic waveform, it might look something like this. So this is P of t, this is t. So I have some DC value here. And then superimposed on top of that, might be something like this, where this is supposed to be sinusoidal. I apologize for making it look crappy because I can't draw. Okay. Where this height is supposed to be the same as this height. So we have oscillation about some constant DC value. Okay. So without doing a whole bunch of math, A, because I did it back in circuits 1, and B, because it's not entirely necessary, it should be fairly easy to see that the DC contribution to the instantaneous power represents the average power absorbed by whatever load this is. Because exactly half of the time the instantaneous power is above this value, and exactly half of the time the instantaneous power is below this value, and it's symmetric about that DC value. So again, the DC contribution represents the average power that's absorbed by our load in this case. Do we need to or want to go through determining the instantaneous power and by extension average power for resistors, capacitors, inductors, or do you guys all feel comfortable with that? So this is a generic representation. It works for any element or combination of linear elements, but we can fairly easily derive relationships specifically for resistors, inductors, and capacitors because we understand what the relationship between between VM and IM is. We went through that when we did our phasor domain relationship. And we also understand, or at least we're supposed to understand, what the relationship between theta V and theta I is for those elements as well. Okay. So I'm going to ask you again, do you want me to explicitly tell you what those relationships are, or are we good? Okay. All right. So for a resistor, we know a couple of things, right? We know that VM is equal to IM times the resistor value. That's just from Ohm's law. And we know that theta V is exactly equal to theta I. So from this, we could see that the average power absorbed by a resistor is going to be 1/2 VM squared over R multiplied by a factor of 1 plus cosine twice omega t plus twice theta V. I got here by saying that since IM is simply VM over R, VM times VM over R gives me VM squared over R. Cosine of theta V minus theta V is the cosine of 0, which is exactly equal to 1, which is where this guy came from. And then on this side, theta V plus theta V is simply twice theta V. So we can now determine the instantaneous power and the average power absorbed by a resistor, only knowing the voltage drop across the resistor, right? Where the average power is actually just this 1/2 VM squared over R term. So this is the DC part and then the DC part gets multiplied by an AC part. So we should see that for a resistor, we're going to have a graph similar to this, except it's going to be shifted up such that the negative peaks correspond to hitting the horizontal axis. The reason why that's the case, and it should be fairly obvious, is that if we go below the horizontal axis, that means that we are actually supplying some amount of instantaneous power, and resistors are literally incapable of doing that. So the smallest value of the power absorbed by a resistor has to be 0. So just imagine this literally shifted up, and that's what it's going to look like. It's going to be symmetrical about that DC value, and it can never be a negative quantity. We could put it in terms of our current as well. So the instantaneous power absorbed by a resistor in terms of current is 1/2 Im squared times R, 1 plus cosine twice omega t plus twice theta I. Another thing that we can point out here, the average power term is literally just 1/2 our DC circuit relationship, right? So in a DC circuit, we know that the power absorbed by a resistor can be expressed as V squared over R or I squared times R. In a steady state sinusoidal or AC circuit, we have this extra factor of 1/2 that just comes from this trig identity because we're multiplying cosine functions. So are we all good regarding the behavior of a resistor? All right. So for an inductor, we know that Vm is equal to omega L times Im. And we know that theta V is equal to theta I plus 90 degrees, which means theta V is always 90 degrees more positive than theta I. So the current is always lagging the voltage. So I'll make sure I'm getting the right relationship here. So from this, the instantaneous power absorbed by an inductor is going to be 1/2 Vm squared over omega L times cosine twice omega t plus twice theta V minus 90 degrees, or Im squared omega, or 1/2 Im squared omega L cosine twice omega t plus twice theta I plus 90 degrees. Let me make sure that L looks very L-like here. So, Cheston, based on the results here, what's the average power absorbed by an inductor?
0. There's no DC also.
Exactly right. So the average power absorbed by an inductor is 0. So that means exactly half of the time it's supplying power, exactly half of the time it's absorbing power. For capacitors, we know that Im is equal to omega c multiplied by Vm, and we know that theta I is equal to theta V plus 90 degrees. And from this, the instantaneous power absorbed by a capacitor is 1/2 Vm squared omega c cosine twice omega t plus twice theta v plus 90 degrees, or 1/2 Im squared over omega c cosine twice omega t plus twice theta I minus 90 degrees.
The theta I is equal to theta v plus 90 degrees.
Yes, theta I is equal to theta v plus 90 degrees. So for a capacitor, the current is always 90 degrees ahead of the voltage, so the current is leading. All right, so those are our instantaneous power relationships for our specific elements. For sources and combinations of elements that can't simply be classified or lumped into a single resistance or single equivalent capacitance or single equivalent inductance, we have to go back and rely on the generic relationship, which is where all of these guys came from. So if you ever have to remember anything, that first equation is the one to remember because it's applicable in all situations. All right, so I'm not going to bother deriving relationships for average power because we can literally just read these off the graph. So what I'm considering now is whether I want to do maximum average power transfer or instantaneous power for multi-frequency circuits now. Let's do multi-frequency power first. Okay. So let's take our generic element slash network. Let's say that we have a voltage V of t across it, current I of t flowing through it. And again, we know that P is simply V times I, right? What if V of t was now a waveform Vm1 cosine omega 1t plus theta V1 plus Vm2 cosine omega 2t plus theta V2, so that we have some multi-frequency response across our element. We're just going to leave it as only two discrete frequencies here because it's just going to make the math ridiculous if we go anywhere past this. And I of t would then be of the form Im1 cosine omega 1t plus theta I1 plus Im2 cosine omega 2t plus theta I. When we multiply these guys together, we're going to get something pretty ugly pretty quick. It will reduce down by a bit, but I'm going to label these guys. So I'm going to call this part V1, this part V2, this part I1, and this part I2, so that we can easily see power is going to be V1 I1 plus V1 I2 plus V2 I1 plus V2 I2. So I'm simply multiplying these guys together. And I'm going to be using that trig identity that we introduced a couple of minutes ago. Cosine angle 1 times cosine angle 2 is equal to 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. Looks like 4 times here. So it's going to get ugly, but like I said, we're going to be able to reduce a couple of things. So if we take the V1 times I1 part, that should hopefully obviously be VM1 IM1 cosine theta V1 minus theta I1 plus 1/2 VM1 IM1 cosine twice omega 1 t plus theta V1 plus theta I1. Okay. So this is the exact same result as what we did a couple of minutes ago, where we just have a single frequency being multiplied by the same frequency term. Okay, so nothing particularly wild or crazy here. Our next portion is going to be V1 multiplied by I2. So this one's going to be a little bit more wonky, okay? So the V1 contribution, we're going to have plus 1/2 VM1 IM2. And now we have to pay a little bit of attention, right? So this is angle 1, omega 1t plus theta V1. This is angle 2, omega 2t. So we can see that we're actually going to have omega 1 minus omega 2 multiplied by time. And then we're going to have theta V1 minus theta I2. And now we have to do the part where we add the angles together. That's going to be 1/2 VM1 IM2 cosine omega 1 plus omega 2 t plus theta V1 plus theta V2. Sorry, yes, I apologize. That is supposed to be theta I2. Thank you, Ian. Now we have the V2 times I1 term. So that's going to be very similar here, except that effectively we're going to have omega 2s minus omega 1s. So that's going to be 1/2 VM2 IM1 cosine omega 2 minus omega 1t plus theta V2 minus theta I1 plus 1/2 VM. Sorry, this should be VM1 up here. This should be VM2 down here. IM1 cosine omega 2 plus omega 1 e plus theta V2 plus theta I2. And then finally down here, we have the the voltage at omega 2 multiplied by the current at omega 2. And so that's going to look very similar to our first expression, where we have 1/2 Vm2 Im2 cosine theta V2 minus theta I2 plus 1/2 Vm2 Im2 cosine twice omega 2, twice omega 2 times t plus theta V2 plus theta I2. All right, so there are actually simplifications that can be made here using the fact that cosine of x and cosine of negative x are the same function. Right, so cosine of x is equal to cosine of negative x. So with that in mind, cosine omega 1 minus omega 2 is the same as cosine negative omega 1 minus omega 2 minus plus. So effectively, we fix the sign here. So effectively, the difference terms are going to add together and create oscillations at a single frequency. These guys here, omega 1 plus omega 2 is obviously the same as omega 2 plus omega 1. So we have one frequency, two frequencies, three frequencies, so twice omega 1, four frequencies, twice omega 2, and then a fifth frequency, which is the DC terms combined. So if we have input signals that are oscillating at exactly two frequencies, our power is a combination of 5 different frequency terms, okay? So it gets a little untenable pretty quickly, but the average power part is fairly straightforward, okay? The average power is just 1/2 Vm1 Im1 cosine theta V1 minus theta I1 plus 1/2 Vm2 Im2 cosine theta V2 minus theta I2. What's interesting about this is that that is the exact result we would get for the power using superposition. Incorrectly, technically, because superposition shouldn't work for power quantities, because power inherently is nonlinear. Right? If you recall, superposition is all about having a linear network, and you can turn off voltage sources and current sources and all that kind of good stuff. But here, even though we have what should be a nonlinear relationship, since it's a product of voltage and current, superposition will work because all of these cross frequency terms have an average value of 0 because they're all simple sinusoids. And over time, the value of a sinusoid, or the average value of a sinusoid is 0. So I'm just going to put underline here and here to let you know which parts make up the average power. And if you ever need to do an average power calculation, you can just evaluate the circuit at one frequency, evaluate the circuit at the second frequency, and combine the results. You're good to go. All right. Now let's talk about maximum average power transfer. And this will be our last topic for the day. I hear whisperings. Does anybody need a question answered? All right. Okay, so let's revisit very quickly maximum power transfer in DC circuits. Okay, so in a DC circuit, when we had a situation like this, where we had a Thevenin equivalent circuit of any linear network we were interested in, and we connected that Thevenin equivalent network to some load resistance RL, we could observe a voltage drop VL across the load and a current IL flowing through the load. The average, or excuse me, the power absorbed by our load was simply VL times IL, which was nothing more than V Thevenin times RL divided by R Thevenin plus RL. So that's just me using voltage division to get the voltage drop over my load resistor. And the current flowing through my load resistor is just V Thevenin over R Thevenin plus RL. And I can easily see then that I get a result of V Thevenin squared times RL divided by R Thevenin plus RL quantity squared. So this is generically what the power in such a system, or the power delivered to the load resistor in such a system would be, okay? Where we've replaced literally any linear network with its Thevenin equivalent. So let me ask you guys a question. We wanted to determine the value of RL that delivers the maximum amount of power, or that has the maximum amount of power delivered to it. What was that value? RL is equal to R Thevenin. So maximum power transfer occurs when RL is equal to R Thevenin, and we got there by taking this equation and taking the derivative, setting it equal to 0, and then finding when the peak occurs, right? So max power occurs at RL is equal to R Thevenin, and the maximum power transferred is equal to 1/4 V Thevenin squared over R Thevenin. So that's how it works for a DC circuit. In an AC circuit, things are going to be a little bit different. Okay. So let's say that we have a very similar circuit. Except now we have some phasor voltage, V Thevenin, and some equivalent impedance, Z Thevenin, connected to some load, ZL. This is our phasor voltage VL. This is our phasor current IL. What's the average power delivered to this load? So PL average is going to be 1/2 times the magnitude of the load voltage times the magnitude of the load current times cosine theta VL minus theta IL. This is literally the average power relationship that we came up with at the beginning of the class. Okay. Our average power is 1/2 Vm Im cosine theta V minus theta I, where we're explicitly stating that the voltage that we're interested in is the phasor voltage VL, and the current we're interested in is the phasor current IL. Everybody okay with that? So what we're going to do is we're effectively going to pick this equation apart and see if we can figure out what each of these little bits are going to be. Okay. So what I mean by that, we can see that phasor voltage VL is the phasor voltage V Thevenin multiplied by ZL over Z Thevenin plus ZL, just using voltage division like we did in the DC circuit above. But now I'm going to break things down. I'm going to use a rectangular form representation for my impedances. So this is going to be V Thevenin times RL plus JXL, all divided by R Thevenin plus JX Thevenin plus RL plus JXL. This is a complex number. I need to get the magnitude of it. And I would find that the magnitude of my voltage VL is the magnitude of my Thevenin voltage times the square root of RL squared plus XL squared divided by the square root of R Thevenin plus RL squared plus X Thevenin plus XL quantity squared. To get my current IL, I can just use Ohm's law. So that's simply going to be V Thevenin divided by Z Thevenin plus ZL. And again, I'm going to expand my impedances into their rectangular form equivalents. So that's going to be V Thevenin divided by R Thevenin plus JX Thevenin plus RL plus JXL. And I can take the magnitude of this guy and find that I get the magnitude V Thevenin divided by the square root of R Thevenin plus RL quantity squared plus X Thevenin plus XL quantity squared. So I figured out what this bit is. I figured out what this bit is. Cosine theta VL minus theta IL is going to be a little bit more difficult. Okay, not a whole heck of a lot, but we're going to have to rely on some trick. So I'm going to draw something here, and I'm just making an assumption. It's not going to particularly matter in this case, but I'm making an assumption that my impedance ZL is inductive. So it has some real part that's positive and some imaginary part that's positive, such that ZL looks something like this on a complex plane, where the projection is onto the real axis is RL, the projection onto the imaginary axis is XL, and the angle that's formed here, theta ZL, is exactly theta VL minus theta IL, by definition for an impedance, right? So the cosine of this angle is the real part divided by the magnitude, right? So cosine theta ZL, which is the same as cosine theta VL minus theta IL, is equal to the real part of my impedance, RL, divided by the magnitude of my impedance, which we know to simply be the square root of RL squared plus XL squared. So from these relationships, I'm going to have to go to the next page here. So I'm going to let you guys finish copying things down. From these relationships, we can substitute in and find that PL average is 1/2 times, let me do the denominator here first, square root of R Thevenin plus RL quantity squared plus X Thevenin plus XL quantity squared. Square root here. Then I'll do my numerator. Magnitude of V Thevenin times the square root of RL squared plus XL squared. That's theta V. Now I'm going to do theta I. So I have that same denominator. My numerator, I just have the magnitude of V Thevenin. And then I substitute in my relationship for the cosine of theta VL minus theta IL. So here I will have just the square root of RL squared plus XL squared, a factor of RL on top, and I can see this guy and this guy cancel out. And I have the square root of some number multiplied by the square root of the exact same number. So those square roots are going to cancel each other out. And so what this leaves me with is 1/2 R Thevenin plus RL quantity squared plus X Thevenin plus XL quantity squared. In the denominator, in the numerator, I have the magnitude of my Thevenin voltage squared times RL. So this form right here is the quantity that we are going to try to maximize. All right. So let me ask you guys a question. If we have literally any reactants in the system, does the average power go up or down? Down, right? Since the reactive power term is in the denominator, if X thevenin or XL is non-zero, inherently, that's going to make our average power decrease. So for maximum average power transfer to occur, what does the relationship between X thevenin and XL need to be?
Or
They need to add together to make zero, which means XL needs to be exactly equal to negative X thevenin. Okay. The maximum average power transfer requires XL is equal to negative. That's only a part of it, right? So under that constraint, PL average, I'm going to call this prime, becomes 1/2 R thevenin plus RL quantity squared divided, or excuse me, that's the denominator. And then here in the numerator, I have V thevenin squared RL. So this is the thing that we need to maximize now. If we ignore this factor of 1/2, this is literally the exact same thing that we maximize in a DC case. So for maximum average power transfer to occur requires RL to be exactly equal to R thevenin. From this, we can say that maximum average power transfer occurs when RL is equal, ZL is equal to R thevenin minus J X thevenin, which is simply the complex conjugate of Z thevenin. And maximum average power transfer equation then is simply 1/8 V thevenin squared divided by RL. So it's effectively the exact same thing as our DC, except that we still have to include that extra factor of 1/2. All right, that's enough out of me for today.